Hello everyone, welcome back to our course. Next, we are going to introduce a very famous distributed coordination surface, which is called ZooKeeper. Again, first is the ZooKeeper overview. As we can see, the ZooKeeper distributed surface framework is used to solve some data management problems that are frequently encountered in distributed applications and provides distributed and highly available coordination surface capabilities. Here, the data management problem is also known as the single point of failures. Because in Hadoop, many services are deployed in the master and slave architecture, and in this case, the master node is a single point that is vulnerable. Therefore, we need to deploy an active master node at working and meanwhile prepare some standby master nodes in case that there was something wrong with the active one. And how to manage the active and standby status, and how to elect a new active master if the old one was broken. That is the responsibility of ZooKeeper. So here we say, as a bottom layer component, ZooKeeper is widely used and depended by up layer components such as Kafka, HDFS, HBase, and Storm. In short, if there is a master and slave architecture and we need to make sure the high availability of our cluster, then we can use ZooKeeper for help. And to be more specific, there is a figure showing the model of ZooKeeper. The ZooKeeper cluster consists of a group of server nodes. In this group, there is only one leader, and other nodes are all followers. When a client is connected to the ZooKeeper cluster and initiates a write request, the request is sent to the leader. After receiving a data change request, the leader node writes the data to the disk first and then to the memory. Then data changes on the leader node are synchronized to the followers in the cluster. But which is the leader? In fact, ZooKeeper can elect its own leader during the cluster startup. Namely, we even don't need to make configurations. Then the leader can be elected automatically. And moreover, ZooKeeper adopts a protocol named ZooKeeper Atomic Broadcast, which ensures the data or status consistency among nodes in the coordination system. Followers use ZAB to synchronize data from the leader and then provide services based on local storage. Finally, we say that after receiving the data change request, the leader node writes data to the disk and then to the memory. This again a little bit strange, because in many other cases, data is written into memory first, then to disks. But ZooKeeper writes data into disks first to guarantee the highest stability, then to memory for efficiency. So we know that there should be a leader in the cluster, and the leader needs to be elected out. During leader election, if an instance obtains more than half of the votes, the instance becomes the leader. Therefore, the number of votes for a leader has a minimum threshold. Then it gives the definition of DR capacity. So what is DR capacity indeed? This suggests the maximum number of 40 nodes in ZooKeeper cluster. So for a ZooKeeper cluster with n servers, n may be an odd or even number. When n is an odd number, for example, assume that n equals to 5, then how many votes at least for a leader? By calculation, we know that at least 3, right? And the server can vote for itself as well, which means that it needs support from at least 2 of its allies. So 5 servers. Now, suppose that the first 3 votes for it, then the opinion from the rest 2 seems not so important. So now they can be 40. Therefore, the DR capacity in this case is 2. And when n is an even number, suppose that n equals to 6, then how many votes at least for a leader? Remember, more than half, so at least 4. In this case, suppose that 4 servers vote for the same leader, and the opinion from the rest 2 is again not so important. In this case, the DR capacity is still 2. And the slide gives us a more general formula, and maybe you can find out that the DR capacity of 5 nodes is the same as that of 6 nodes. So why bother deploy 6 nodes? Considering the election and the writing speed, it is recommended that an odd number of nodes can be deployed for ZooKeeper, like 3, 5, and 7 nodes are widely used in real industry. Next are some key features of ZooKeeper. First is the eventual consistency. It means that all servers are displayed in the same view. We will show you the reading process of ZooKeeper, and the eventual consistency property plays an important role in the reading process. Second is its real-time capacity. Clients can obtain server updates and failures within a specified period of time. Namely, we don't need to wait for too long. Third is reliability. ZooKeeper is very humble, and all servers, regardless of leaders or followers, are friendly to each other. So once a message is received by one server, it will be received by the rest of all servers. Fourth is wait-free feature. Slow or faulty clients do not intervene the requests of rapid clients, so that the requests of each client can be processed efficiently. This is to say that different ZooKeeper clients are independent, so they do not affect each other. Fifth is atomicity. It means that data update either succeeds or fails. There are no intermediate states. Last is the sequence consistency. It means updates sent by the client are applied in the sequence in which they are sent. Namely, the applications uploaded by the same client is in sequence, first in, first out. Please pay attention. We emphasize that for the same client, ZooKeeper shows sequence consistency. But for different clients, it shows wait-free. So don't be confused of the different features of it. And finally, we can show you 2 important processes of ZooKeeper. Reading is relatively easier, so we can have a look at it first. And as we mentioned before, ZooKeeper has eventual consistency, so it does not care about which server the client is connected to. For example, the client is connected to ZK1, which is a follower, But it doesn't matter because the data keeps synchronized within all servers in this cluster. So the client will always get the same result. Therefore, read operations can be performed between the client and any node. But for writing, it may be a little bit more complicated. Here, the process follows as these steps. Firstly, again, a client can initiate a write request to any server, for example, ZK3 right now. After ZK3 receives the request and the data, it reports its request to the leader. After receiving the write request, the leader broadcasts the write request to all nodes and confirms whether the write operation can be performed. Then, all followers send ACK messages to report whether it agrees or not. The leader determines whether the write operation can be performed based on the ACK messages. If the majority of the servers agree to write the data, then the write operation can be performed. Now, the leader sends the request to the followers and performs the write operation. In this case, data is written into leader first, then synchronized to the followers. After synchronization, the write operation is complete, and the client gets a response that the write request succeeds. And likewise, if the majority says no, then the whole cluster refused to write data, and thus the client will get a failure result. Alright, that's all for this chapter. In this chapter, we introduced what is ZooKeeper, the service architecture of ZooKeeper, and some key features of ZooKeeper. Thanks for listening, and hope you guys enjoy all the contents we introduced so far. If you find the course interesting, we hope that you can put more efforts for further learning in your leisure time. After all, this course just helps to lead you to the techniques of Hadoop. Again, wish you enjoy it and wish you all the best.